All right, guys, part 2 of our correlation videos. And this one, we really want to talk more about the actual correlation itself. What is a correlation? Well, honestly, the word's pretty damn intuitive. Break it up, you got correlation, right? Multiple things, relation, how they are related, how they are associated, how they are similar or different in some way. It basically says, when one variable increases, does the other one tend to increase? Or when one variable increases, does the other one tend to decrease? Or is there no relationship whatsoever between the two of them? Right? That's the essence of a correlation. So take a real simple one. When temperature goes up, guess what happens? It not only gets hot outside, but I know another variable that increases at the exact same time. So I'll bet you know this one too. If you were to go to, let's say, Belle Isle, right now, today, so today is February 4th, I believe. So if you were to go to Belle Isle today on February 4th, it's cold. It's in fact, I think, about freezing temperature outside. How many people do you think you would find on the beach at Belle Isle? Not many, right? Pretty close to zero. Let's just assume zero. And let's just go ahead and say, using Celsius just for fun, so we have the same number, it's zero outside. Now, as this temperature goes from zero up to 15, 16, 17, 18, 19, 20, I don't know, Celsius, let's go back to Fahrenheit. If it's 80 or 90 degrees outside, guess what happens as this goes up? This other variable that's counting the number of people at the beach also goes up. And so as temperature goes up, number of people at the beach goes up. It's not magic. It's just that the two are correlated. When one increases, the other increases. We actually have a statistic to calculate and to quantify the degree to which two things can be related, and we call it the Pearson correlation coefficient. We usually just call it a correlation, but it's to distinguish between the Pearson and other forms of correlation. So Carl Pearson came up with the correlation coefficient. We symbolize it using a lowercase r, right? And it measures the strength of a linear relationship, right? Straight line relationships between two variables. Now, I'll show you in a second that not all relationships are relatively straight line, and so we sometimes have to use other measures for those types of relationships. But the Pearson correlation coefficient's the one we like, the one we're going to teach about in here, and it's got some real simple characteristics, right? It's almost always expressed as a decimal, right? In fact, it can only range between -1 and +1. That's the entire range of correlation. If it's a +1, it's a perfectly positive correlation, right? The degree to which it is close to 1, in fact, indicates the strength or magnitude of that correlation. The closer it is to 1, the stronger it is. The closer it is to -1, the stronger it is towards a negative correlation. The closer it is to 0, the stronger an indication that there is no relationship whatsoever. So a good, easy way to catch yourself if you happen to be calculating a correlation coefficient and you get all the way done and you say, haha, my R is equal to 1.3, then you should immediately say, no, it's not, because correlations cannot be above 1. They cannot be below -1, and so I've made an error and I need to go back and fix it. Okay, so we're an easy way to sort of catch yourself. Some examples of positive correlations. These are existing positive correlations. Now, that doesn't mean they're meaningful, right? So per capita consumption of mozzarella cheese. How much cheese is consumed as a function of the population, not just an overall amount of mozzarella cheese, is positively correlated with the number of civil engineering doctorates that are awarded. That is, in areas that consume more mozzarella cheese, they also award more civil engineering doctorates. One goes up, the other one goes up. U.S. spending on space, science, technology is correlated with suicides by hanging, strangulation, and suffocation. Just because one goes up and the other goes up doesn't mean one caused the other one. In fact, the number of people who drowned by falling into a pool and films Nicolas Cage appeared in, okay, that one actually makes a little bit of sense. People are probably jumping into a pool every time a Nicolas Cage film comes out, and maybe that's why these two are related. No, these are just examples of two things, right, in each case, that increased at the same time. Because they were increasing at the same time and decreasing at the same time, they followed each other perfectly. That's what we call a positive correlation. When they go in opposite directions, so when your R value is less than 0 and above or equal to -1, that's when these two things tend to go in opposite directions. And this isn't a great example of a negative correlation because they don't diverge too much here. But the idea would be that as one increased, the other one might decrease. So as The number of people who drowned after falling out of a fishing boat decreased. The marriage rate in Kentucky increased. So perhaps as the number of people who drowned after falling out of a fishing boat decreased, it's because they no longer drowned falling out of a fishing boat, that they could get married. And so as one went down, the other one went up. So we don't need to look through a whole bunch of these examples. There's no correlations as well, right? Cases where there's zero relationship between the two things. When we see these in what are called scatter plots, the dots look like they're all over the place, right? They just don't seem to fit any particular pattern. And so looking at something like how worldwide non-commercial space launches are correlated with sociology doctorates awarded in the US, those aren't actually correlated in most situations. And if you look at sociology doctorates worldwide, there's no relationship whatsoever. As one increases, the other neither increases nor decreases. That is, there is no correlation. Now, it's important to note that just because you find a Pearson correlation coefficient of 0 doesn't necessarily mean that two variables are unrelated. So in a sort of squiggly relationship like we see right here, or one like this, the famous Yerkes-Dodson stress performance curve, we see that in the first part of this graph, the line increases steeply and then plateaus at the top and then decreases steeply as well. And so to correlate the change in x and the change in y, we would see that at certain points as x went up, y also went up, right? The first part of the graph. But then at other points, as x continued to go up and y started to go back down, right? Scores started to go back down on y as x continued to increase. And so we have a positive correlation and a negative correlation. So across the entire data set, we have a correlation of 0. But as you can see here, that's not a situation where we have zero relationship between the variables. In Yerkes-Dodson, it's very clear there is a relationship between performance and stress level, right? As stress increases from extremely low levels of stress, such that you are entirely inactive and bored, we begin to improve our performance as we get more energized, more focused. And then after a while of peak performance, we become fatigued, exhausted, and then we eventually hit burnout and breakdown as stress has gone too far and performance is no longer improving. Again, just because you have a correlation of 0 doesn't mean there's no relationship. It just means there's no straight line, linear relationship. And so if you look at scatter plots that plot XY pairs of data, number of siblings, number of pets, number of chickens on a farm, number of daughters the farmer has, whatever they happen to be, when you plot those XY pairs and you draw a line through them that best fits those pairs, if those lines are really tight, the dots are really tight with that line, we have what's called a strong correlation. And if it's because they're both going up, so it looks like an uphill, up and to the right, that's what we call a strong positive correlation. If they're not as close to that line, it'll be a weak correlation. If they're super tight and the line's going down, it's a strong negative correlation, right? So you've got weak, we have moderate, we have strong, and then of course we have no correlation. Now, a researcher named Cohen actually published back in the late 80s a set of guidelines for researchers to consider how big of a correlation was an important size, was a significant size, something we could call a large effect, if you will. Now, unfortunately, these don't play well into behavioral sciences because it's extremely difficult to predict the behavior of a human. You need to know a lot of variables to do so, and so these aren't the best metrics for us, but we don't have no others, so we'll use them right now. So if you calculate a correlation and it's above 0.1 but below 0.3, we'd call it a small correlation. But if it's above 0.3 and still below 0.5, we call it a medium correlation. And then lastly, if it's above 0.5, we call it a large correlation. So anywhere from 0.5 all the way to 1 would be a large effect, right? A strong correlation. So let's watch a quick video on this.
Chocolate. Like many of us today, chances are you already ate some. Dark, milk, or white, filled with praline, vanilla cream, or marzipan. Almost everyone has a favorite type. Albert, my cat, never really understood why humans are so fond of the stuff. Even though most of them will deny it, the large amount of sugar in chocolate is one of the main reasons it has grown so popular. And Albert, like all cats, cannot taste sugar. While we're at it, what exactly is chocolate made of? Milk chocolate, by far the most consumed type of chocolate, is, per 100 grams, made of 51 grams of sugar, 30 grams of fat, 8 grams of carbohydrates that are not sugar, 7.6 grams of protein, some water, a bit of potassium, phosphorus, theobromine, calcium, and finally, of many other things that weigh even less, such as vitamins, caffeine, etc. Oh, the benefits of chocolate. You often hear about them in the press. A few years ago, it was not possible to miss something that was on most press covers. Eating chocolate would not only improve your health, but also your intelligence. While Chocophiles were delighted by this news, and chocolate magnates around the world were rubbing their hands due to this unexpected free publicity, statisticians were busy hitting their head against a wall and taking pills. So, what happened? While chocolate is something a lot of people are fond of, the research paper that got the press excited a few years ago never proved that eating chocolate would improve your intelligence. The researchers behind the paper just discovered a correlation that they published in 2012. Let's take a look at their research. What they analyzed is the chocolate consumption per capita in a set of countries and the number of Nobel Prizes received per capita in the same set of countries. And what happens when you make a graph of all this? Something impossible to miss appears. The more country inhabitants consume chocolate, the more Nobel Prizes you get in this country. Albert does not understand what's the problem. Eating chocolate helps improve one's intelligence. Isn't the data clear enough? No, Albert, it does not work that way. When a correlation between two variables, A and B, is observed, most people think, naturally, that A causes B, but what most people miss is that B might actually cause A. Regarding chocolate and Nobel Prizes, maybe that each time a country gets a Nobel Prize, its inhabitants celebrate the event with a chocolate orgy. In this scenario, the large consumption of chocolate per capita is the consequence and not the cause of the many Nobel Prizes received in the country. But there is yet another possibility in order to explain the observed correlation between A and B. Maybe that neither A nor B is the consequence of the other, but that a third variable, let's call it C, causes both A and B. Statisticians call C a confounding factor. Aw, are you lost, Albert? Let's try with an example. A team of researchers approaches people in the street. To each person they meet, they offer a candy and ask 2 questions. 1. Did you sleep with your shoes on last night? 2. Did you wake up with a headache this morning? After having gathered hundreds of answers, the researchers start analyzing the data and then observe something remarkable. Those who went to bed with their shoes on were almost always the ones waking up with a terrible headache. For those who went to bed without shoes, waking up with a headache was much rarer. A strong correlation between shoes on and a headache in the morning is thus observed. This correlation is published in a research journal. The press quickly gets interested, and we end up with cover pages such as, "Proven! If you sleep with your shoes on, you'll get a headache!" Of course, sleeping with your shoes on is safe. You won't get a headache from it. Sleeping with your shoes on and waking up in the morning with a terrible headache are both the result from partying too hard during the night. This is our third variable, C, the confounding factor, about which both researchers and journalists should have thought. But everyone was so obsessed with publishing, no one took the time to think. Let's come back to chocolate. Can we figure out an obvious confounding factor that would explain the observed correlation between chocolate and Nobel Prizes? What do you think, Albert? Think hard. I'm sure you can figure it out. You still have a few seconds. Well done, Albert. What matters here is wealth. The wealthier a country is, the more it will be able to spend on education and research, thus doing its best to support its brightest citizens towards a Nobel Prize. At the same time, in such a country, people can usually afford chocolate, which is still a luxury for most people in the world. What should you remember from all this? That the world is an insanely complex place, and that, unfortunately, discovering a correlation between two things is not always enough to conclude anything. Too often, though, we forget about this. Remember, Albert, when two things are correlated, it does not necessarily mean that one is causing the other. This video was made possible thanks to the passion of the people behind Albert. If you love Albert as much as we do and want to see more of him, there is something fairly simple you can do to keep us motivated. Talk about him around you and subscribe to his YouTube channel. See you soon.
Okay, so just because it's a correlation doesn't mean it's a causation, right? Correlations just mean they're related, doesn't mean one is producing the effect of the other one. And we see sort of illusory correlations all the time. People that see horoscopes and elements of the horoscope fitting elements of their life, they see the parts that match through a sort of confirmation bias, and that leads to this belief that these two things are related. The accuracy of the horoscope and the events of your particular life are highly related. Illusory correlations are so common that we can use them to almost convince people of sort of age-old stories about how storks bring babies. So this is actually true after World War I, and this has been the case a couple of times over. But at least in this instance, after World War I, there was a strong positive correlation between the population and the number of storks in Oldenburg, Germany. So the population of human beings, as it went up, so did the population of storks in Oldenburg, Germany. I think we all know why. right? Storks bring babies. More storks, more babies. More babies, higher population. It's as simple as that. Correlation must equal causation. No, of course not, right? You know that. Just because these two variables are correlated, one didn't cause the other. In this case, it's probably things like increasing population after a war means more buildings, things like that. Means more baby makers because after a war you need more babies because you've just killed off some of your population. More buildings actually means more nesting sites for storks because they love those little sort of enclaves that they can find between buildings. And so the simple causal variable here is growth, right? Post-war growth led to more buildings, which led to storks, led to more baby makers because they were making babies because they're not at war anymore, they're at home making babies. And correlation does not equal causation. That being said, this one may give me a second of pause here. It turns out that murder rates, especially in New York City, but a couple other places as well, are positively correlated with ice cream sales. I shit you not. I don't know if it's this guy's fault or what's going on here, but as ice creams is sold more, murder increases. I don't know, guys. I'm freaked out.
If you look at the stats alone, eating ice cream and murders in New York are positively correlated. This means that the more ice cream sold per person, the number of murders increases. Vanilla bean never seemed so scary, right? Before you stop eating ice cream sundaes to save innocent lives, think about it. Correlation as a statistic doesn't explain how or why the relationship between ice cream and murder exists. It simply shows that it does. Causation makes an even bolder assumption and says that a change in the number of chocolate cones sold will cause a change in the number of people who meet their unfortunate end. This is clearly a big leap. A well-designed experiment will rule out other factors that could be related. So you must ask yourself, what's another variable at play? It turns out that temperature was also correlated with both ice cream sales and murders because the numbers for both spike during the summer months. When it's warm outside, people simply get out of the house more. They're on summer break or vacation and want a cold, delicious treat. Kids hang out unsupervised more. It just so happens that the Freddy Kruegers of the world also get out more during the summer. Before you jump to a cause and effect relationship when a correlation is found, look at how the data was collected and consider other related factors. And go ahead, eat that pint of Rocky Road.
Okay, so I think you get the idea of correlation not equal causation. The hard part is identifying it in your own thinking. When you see two things that are truly only being correlated, being able to remind yourself that there was no experiment being conducted here. This is simply observing a relationship, and therefore you have to be cautious assuming those two variables to be causally related in any way whatsoever. All right, so that's it. Now let's calculate a correlation. Cheers.